Okay, welcome class to Biophysics class 31. And we're going to start studying transport of ions and across cell membranes with an eye to eventually understanding the action potential in nerve cells. That's going to be our final goal this semester, is to understand the process of the action potential by which nerve signals are sent. But first, we have to build up some initial concepts. Um, so we're going to introduce something called the Nernst potential and a related concept which uses the Nernst potential called the Donnan equilibrium, as we start to understand how ions um, exist on either side of the cell membrane. So the Nernst potential has to do with balancing a concentration gradient and an electrical force. So let's explain that with an illustration here. Here we have a cell. We pretend there's just um, one ion in it, which is potassium here, and it has a larger molarity, a larger concentration inside the cell than outside the cell. So the naturally the potassium would like to diffuse in the direction of this chemical gradient from higher to lower concentration. But um, for reasons we'll eventually understand, the inside of a cell is typically at a lower voltage than the outside of a cell. And this is called the membrane potential. So you can see that indicated by these pluses here and minuses here. So there's a minus inside the cell, which indicates that the membrane potential would be negative. The inside, the potential inside minus the potential outside would be negative. Um, so as I said, the potassium ions would normally diffuse out of the cell, but because of this um, membrane potential, there's a force due to these electrical. There's an electrical force in which always points from positive voltage to negative voltage, which acts uh, against the flow, okay, in the opposite direction from left to right. So there's a balance of the chemical gradient and the electrical gradient or electrical force. And so then what we call the Nernst potential is the voltage difference between the inside and the outside of the cell that's required to maintain a given concentration difference for an ion against the ion's natural tendency to diffuse. Okay, so depending on how uh, ion is, the ion's concentration differs inside versus outside of the cell, we would expect more or less of a potential required to counter um, the tendency to diffuse along the chemical gradient. Okay, so how do we calculate this Nernst potential, this voltage difference that we need to counter the tendency to diffuse? So here's a short derivation for an ion with a charge Q and concentrations C outside the cell, so that would be 5 millimolars here for potassium, and C inside the cell, that would be 140 millimolars in this case up here. So we start off by saying the the sort of traffic cop for movement of materials is the chemical potential, and that still holds here. So we'll have a balance when the chemical potential inside is equal to the chemical potential outside for this given ion. All right, so then this expression, the first part of this expression, mu in, was from our previous work, was equal to kBt log Cn over C0 plus the reference potential. Okay, so that's what we found for the chemical potential of a ideal gas or a dilute solution. but we add in now an energy having to do with the electrical force, which would be the ion charge times the um, voltage or the electric potential. So this would be the electrical potential energy, which figures in with the chemical potential through the energy through the chemical potential in this balance. And similarly, on the outside, we have the same terms, the chemical potential here of a dilute solution, plus the electrical potential energy due to the ion being present in a an electrical potential outside the cell. Okay, so this would be the balance here, and then we notice we can cross off the reference potential from both sides, and we have common factors of Q here. So if we take Q times V in minus V out, and then subtract KB log C in over C0 from the right side, we get this right here, okay? And then finally, we can use properties of logarithms. Log of A minus B is log of A over B. So this is C out over C0 divided by C in over C0, or just C out over C in. So solving for V in minus V out, we get, which is the membrane potential, the potential inside the cell minus that outside the cell. We find it's equal to kBT over Q times the natural log of C out over C in. Okay, so again, this is the membrane potential, which is typically a negative value in the cells in our bodies and in animals. And this is the definition of the Nernst potential, kBT over Q times the log of C out over C in. So if we reverse this chain of reasoning, if the membrane potential is equal to the Nernst potential for a given ion, then the concentration C out and C in will remain constant. Let's see. So, okay. So that's the Nernst potential. What is the Donnan equilibrium? The Donnan equilibrium occurs when there are multiple ion species and macromolecules involved. Okay, so typically we have inside the cell proteins and carbohydrates and so forth, which are too big to diffuse through the cell membrane. And so we have negatively charged macromolecules trapped inside the cell, and they have a negative charge density, rho macro. Okay, and then we have now we have multiple ions for the Donnan equilibrium, multiple ion species. We have key ions and sodium, potassium, and chlorine, which can cross the cell membrane. And it turns out the typical concentrations of these ions outside the cell are, in millimolars, 140, 10, and 150. And notice that since sodium and potassium are positive and chlorine is negative, 140 plus 10 minus 150 is 0. So that's an overall neutral solution outside of the cell, which is what we would expect. We don't expect a charged solution. Charges tend to redistribute if they get if charge builds up in a certain location. So what we'd like to do is solve for the 3 ion concentrations inside the cell, as well as the membrane potential delta V. Okay, because we have we have the concentrations outside the cell, and we know there's a membrane potential across the cell. And we also know that in order that these ions are in equilibrium, from the definition of the Nernst potential, the membrane potential must equal the Nernst potential of each ion for each of their concentrations to be stable inside and outside the cell. If the membrane potential is different from the Nernst potential for a given ion, that ion will flow in one direction or the other. So, okay. So the equations we set up are neutrality of the solution inside, which would be the concentration inside of sodium plus that of potassium, minus the concentration of chlorine, since that's a negative ion. So this is a charge equation, plus the charge density of the macromolecules, which we're taking here just to be proteins, divided by the elementary charge to put it into concentration instead of charge per unit volume, to put it in terms of molecules per unit volume. And for the membrane potential, we set the membrane potential delta V, which is V in over here minus V out, equal to the Nernst potential of each of the three ions, sodium, potassium, and chlorine. Okay, and so that's 1, 2, 3, and 4 equations, and we have 4 unknowns, which are the 3 ion concentrations inside the cell and the membrane potential delta V. And the result of solving these 4 equations and 4 unknowns is actually gives delta V as minus 10 millivolts. Okay, so the membrane potential is minus 10 millivolts, and the concentrations inside the cell of 210, 15, and 100 for sodium, potassium, and chlorine, respectively. Okay, and if you'd like to see the details of that solution, you can check out our textbook, solving these 4 equations and plugging in all these numbers. Okay, so so how does the Donnan equilibrium do in describing real cells? So what are the advantages and disadvantages of the Donnan equilibrium approach? Well, we found in solving the Donnan equilibrium that the resting membrane potential was around minus 10 millivolts, which is in decent agreement of the typical with the typical cell value of minus 60 millivolts. At least it's the right sign. Okay, so that counts as a moderate plus. However, the total ion concentration turns out to be greater inside by 25 millimolars. If you go back and look, the sodium and potassium and chlorine inside the cell has a total of 325 millimolars, while that outside the cell, which was the measured amount, is 300. So the difference is 25. And a difference in concentrations results in an osmotic pressure of delta C, 25 millimolars times kBT, which turns out to be a sizable pressure, in fact, enough to burst the cell membrane. So clearly we don't have the whole picture here in using the Donnan equilibrium, even though we've got some rough agreement with the membrane potential, at least that it's negative as it is experimentally found to be negative. In addition, for the squid axon cell, which was one of the first cells to be studied because it's so large, measured values of the Nernst potential for these 3 ions were actually equal to plus 54, minus 75, and minus 59 millivolts. And those are not equal to the membrane potential of around minus 60 millivolts. Okay, especially for the sodium here, plus 54 and minus 60, those those are the opposite signs. The others are sort of close, but that one's way off. So what this indicates is that there must be, since these are not in their natural chemical equilibrium, which they would be if the membrane potential was equal to the Nernst potential, there must be active ion pumps, which keep these ions concentrations out of their natural equilibrium state. And it turns out these ion pumps will play a major role when we study the action potential in nerve cells in a few classes. Okay, next up, in our next class, we'll study an equation called the GHK equation, which improves on the Donnan equilibrium by taking into account the permeability of each ion to the cell membrane. Okay, so we'll see we get a little bit better results there. So overall, what have we learned? We've learned that there's different ion concentrations on either side of cell membranes, that the natural diffusion of the ions is counteracted by a membrane potential, which the cell usually has. We've learned the definition of the Nernst potential as the potential needed to hold a given concentration difference, as the membrane potential needed to hold a given concentration difference of an ion on either parts of the cell. And we've looked at the Donnan equilibrium approach of looking at multiple ions and looked at its advantages and disadvantages. All right, thanks for your attention, and I will see you in class soon.